Okay, so here's our last lesson. Like I just said, do whatever works best for you, right? So I've got about a 45-minute presentation I'm going to give. Yeah, let's get started. Here are some of the things that we've been focusing on so far in our class. I want to do a quick recap just before I move on to these slides here. Is everybody ready to go? So I do want your attention. Or if you're not going to give me attention, at least don't be a distraction, right? Here's a few things that hopefully you're getting familiar with. I don't need you to be perfect at it yet, not my expectation, but you're slowly picking up on. Here's one. Let's say I give you this right here, copper 2960. You know how I've been saying this is like learning a new language? I don't know that I could draw like a Japanese character or a Chinese or Russian character. I know that like in French, sometimes we write like E's with like a little accent on top of them. But like copper 29 here is like the letters of the alphabet I've been teaching you. Hopefully you're getting better at recognition and going, oh, I know what that letter that is. That's copper. And maybe better than that, you know the sounds it makes. You know like how my daughter, I say she's in kindergarten, and she's learning the letter like O or P. You know, there are some letters that have more than one sound, where it can make like an oo or an ah sound if it's an O, right? Well, as you look at this character right here, are you getting better at recognizing that this thing has 29 protons? That it has 31 neutrons? And that if I didn't put anything in this top corner here, it must have 29 electrons as well? Hopefully you're starting to pick up on that, right? And if not, then that's something you should mention to me. Hey, Chris, I need help because I still don't know how this character works. Okay. Here's another thing we've been working on. Let's say we take that copper and we try to combine that copper with chlorine. And we write a formula something like this. Hopefully you're familiar with the fact that this must be the copper that's the +2 version, and this must be the chlorine that's the -1 version. And that's why we need a little 2 in the corner, because we need 2 minuses to counter every positive. Hopefully that's starting to be something you're picking up on. Don't need you to be perfect yet, just need you to work on it. Along those lines, hopefully you're getting better at being able to name that compound. I hope the flow chart on the board is also useful. So if I tell you that the name for this thing is copper, sorry, that's not writing very well, copper Roman numeral 2 chloride. Oh, I've got some lag here. Chloride. Hopefully you're getting better at being able to name these things as well. And then the final thing we've been working on here is being able to then take these compounds that we now can name and being able to write a sentence about them, like say this, copper chloride. Maybe it adds to silver, and then we make a prediction about what's it going to turn into. That's a Cl, by the way. Sorry, my board is a little bit laggy today. What kind of reaction is this going to be? Single replacement. If you're starting to pick up on some of those, what happens is the silver right here is going to trade spots with the copper. That's your single replacement. And what will happen is your silver will now match up with your chlorine, and copper gets booted out all by itself. By the way, I started marking some of the labs that you guys submitted. Quick side note. Nobody's like grossly failing where it's like, oh my goodness, this is horribly wrong. Most of it's pretty good. I've left comments. I haven't marked all of them, but if you want to take a look over the weekend, look for my, my smiley faces, my check marks, my comments. Take a look for feedback. I haven't marked them all yet, though, so I'm sorry if I haven't got to yours. The one thing I would point out, though, some of them weren't finished. I didn't expect them that they had to be. But if you have a long ways to go, keep in mind that that's something you'll need to work with on your team. Use Moodle as a way to talk to your team members and figure out who wants to do what, right? Because if you have 5 questions left to do, if each of you just does 1 question over the weekend, you're done. Is that reasonable? So anyways, that was my side note. One of the things I did notice, though, when I was marking labs is that some kids were forgetting to put down a state of matter. So as an example, silver should probably be solid, and so should copper. That's its standard state of matter. CuCl2, copper 2 chloride, you could probably figure that out by using that table that tells you whether things are aqueous or solid. So if you have that table or know where to find it, I'm pretty sure it's aqueous. And silver and chlorine, I believe, on that table is solid. And then the last thing you'd need to do is make sure that it's balanced. And there's a problem with balancing here. There's 2 chlorines here to 1 over there. So if you put a couple of 2's here, this is balancing an equation. Okay. Hopefully, as I'm describing this is something that like you recognize. Maybe you're not perfect at it yet, but hopefully you're not going, never seen that before. Okay. So those are some of the skills we've been working on up till now. Here's the problem. Every time that we've been talking about an equation, a compound, or a character, right? I think that's really what we're describing, right? A single character, a word where they're put together, or a sentence of some kind here. We're always talking about one or two particles, right? Like, look at this equation we wrote here. I'm telling you that one particle and two particles makes one particle. We're talking about like one atom at a time. That's really small. When we are discussing right here, copper 2 chloride, we're talking about one particle of it. That's one at a time. This copper right here, we're talking about an individual. And that leads us really nicely then into our last topic. It's really inconvenient to count particles one at a time. In fact, it's actually kind of ridiculous. Because are you made of just one particle? You're made of trillions upon billions upon, I'm not even sure how big the number gets, right? But like, things in the real world are made of such a high number of particles, we need a better way of counting them. It's kind of ridiculous to count things one at a time. Okay. So what I want to begin with is actually an analogy of buying food at the grocery store. Imagine that you're going to Costco, Save on Food, Safeway, wherever you buy food. I think we can categorize things in three ways we buy things. We either buy things individually. Like, let's say you go buy one apple. You can go buy one apple. So you can buy things individually. Could you go buy one box of cereal? Sure. Could you go buy one can of soup? Sure. And sometimes that's reasonable to buy one item of something, right? Like one jar of pickles. But in the chemistry world, one atom of copper, I mean, I can't even make my fingers go that small to measure one atom of copper. So often we like to measure things in like a group of some kind. And as an example, this picture of chunky soup here, you could buy like a multi-pack of something. Now, is it possible for you to buy the chunky soup in cans of one at a time as well? Sure, yeah, you could. But there are some things that it's completely unreasonable to buy one at a time of. Like, for example, an egg. Does it really make sense to go to the grocery store and buy one egg? Like, we don't really do it that way, right? We usually need to buy them as a group. What type of packaging do eggs normally get sold in? A dozen is usually the most common, right? The dozen is an example of a group. Let me give you another example. It's similar. Anyone ever heard of a baker's dozen? What's a baker's dozen? Yeah, 13. Yeah, basically the concept was the baker threw in a freebie. You buy 12 donuts, 12 like a dozen, right? And you get an extra one. Here's another example, maybe not about food. Historically, let's say you were like a Roman soldier. If you were a centurion, anybody know what a centurion meant? Ever heard that phrase before? It's a rank. A centurion is the person who, do you know? Anybody else know? You're kind of right. Give it a try. No? Okay. A centurion is the captain of a battalion of 100 people. Yeah. So if you're a centurion, you're not like the lowest grunt person in the Roman army. You're kind of one level up, but you're the person who's in charge of 100 people, right? We actually still use the word century to describe 100 years. Okay. The point I want to make is that it's often logical for us to group things together in a larger chunk. Rather than measuring apples one at a time, we put them in a dozen or in a century or in whatever other word we use. Okay. In chemistry, we actually have a similar concept to that. We call it a mole, and I'm going to talk about that in another slide. But a mole is basically, let's not measure particles one at a time, let's measure a whole bunch of them. Because it's kind of ridiculous to count them one at a time. There's also a third way, though, that we can measure things when we want to measure our particles. And we can measure them by weight or by mass, like by how heavy they are. I'll give you another example here. I think in this picture right here are banana chips. You know those ones that like get dehydrated? A tasty little snack. Would it make sense for you to go to the store and buy one individual banana chip? That makes no sense at all, right? Now, it doesn't really even make sense for you to have to count them out. Like, wouldn't it be ridiculous to go to Save on Foods and to like reach into the bin and count out 20 of them? Like, we just grab a scoop of them, put them in a bag, and then we weigh them, and you pay for them based on their weight. And that's kind of like the last way that we can measure things. It's how heavy they are. Right. Individually is one at a time. You guys okay? Okay. One at a time individually, as a larger multi-pack, or if we need so many of them, let's just weigh them and figure out how much they weigh. My goal today is to try to explain how we use those same principles in chemistry because, like I said to start my lesson here, this right here is one copper atom. This thing right here is one chlorine, copper 1 chloride atom. Sure, I found two, but like, when are we ever going to have just one or two of something? Never. So let me go to my next slide here and talk about the concept of a mole. A mole then is what chemists decide to group particles in, so that the Costco multi-pack comes in a group of, say, 12 or 100. Here's the only problem. In order for it to be useful for us in chemistry, it's not 12, it's not 100. When we group things in chemistry, we put them in groups of this number right here. 602 kabillion, basically. We actually figured it out earlier in class. Someone told me that number is actually 602 sextillion. Is actually the name of that number right there. Leads to the question, why do we group them in that number there? Why not 12? Why not 100? Why not 1,000? Why not something nicer? Okay. Why 12 to a dozen? Why couldn't a dozen have been 15 or 7 or 42? To be honest, sometimes it's kind of random as to what you decide to group things in, right? 100 was a nice round number for a centurion to keep track of. Why couldn't a centurion have kept track of 99 people? I'm sure he could have handled 99 just as easily as 100, right? To be honest, sometimes it's just random. Is that fair? But in science, we actually had a little bit of logic. They decided this number right here, and the reason, oh, my board is glitching out on me here. Hang on a sec. Maybe I walked too far away. You may have to give me a second here. Am I working? Oh, I have to go back to the backup one again. Okay, give me one more minute. If it doesn't work, I'll have to go to the backup board. Okay, I think we're good. Okay, I'm back up. What was I finishing with? Oh, the answer is not random. It's not just that 12 was picked because of some random number, but it's actually right here if you're curious. As a way of trying to define why scientists chose how many to put in their grouping, they based it on 12 grams of carbon-12. I think that was kind of the logic. You know how carbon-12 is the one where there's 12 in the corner here? That's carbon-12. They kind of figured, let's make this 12 right here match this 12 right here. I don't know who was assigned counting particles, because that would have been crazy to have to count this many particles out here. But yeah, they figured out that this is what we're going to make a grouping. Okay. So let me go back to this analogy again. We could buy atoms one at a time, or when we now count them, let's just count them as like the 12 pack of chunky soup, except it's not a 12 pack, it is a 6 kabillion pack. That's all. Okay. I need to do a little mini brief aside lesson. Because of the fact that we're now going to be talking about such large, massive numbers, where there's so many zeros afterwards, we sometimes like to write it in a different notation. Okay. You probably haven't seen this before, because most of my first period class hadn't. But this is called scientific notation, sometimes known as exponential notation. And the concept basically is we're trying to shorten up a number with a lot of zeros. Let me try to give you the short version of how it works. Okay. Let's say that I gave you the number 6 times 10 to the power of 1. 10 to the power of 1 is just 10, right? So 6 times 10 is 60. Okay, stay with me. I'm just going to do a few more. Let's say I gave you 6 times 10 to the power of 2. Well, isn't 10 to the power of 2 just 100? Isn't 6 times 100 then 600? And one more, then I'll get to my point. So 6 times 10 to the 3. Well, isn't 10 to the 3, 10 times 10 times 10, isn't that 1,000? So 6 times 1,000 is 6,000. Okay, here's how this works. Do you see how these numbers right here, the only difference between them is that we're gaining a 0 on the end of them? That's what scientific notation does for us, is by timesing by 10, all we're doing is we're adding an extra 0. 6 has no zeros. By timesing by 10, it has a 0. If you do 6 times by 10 to the 2, this 2 right here tells you how many zeros you have at the end of your number. This 3 right here tells you how many zeros you have at the end of your value. So if I tell you that it's 6 times 10 to the 23, that helps us to know how many zeros come afterwards. But you need to count this out though. 3, 6, 9, 12, 15, 18, 21. Well, the reason why this one's been written slightly differently is that I know there's a 2 right here, but honestly, like we could probably round that and just call it, rather than 602 kabillion, let's just call it 600 kabillion. Pretend that's more or less a 0. Well, now that we're 21, 22, 23, it's basically 23 zeros afterwards. I know there's a 2 right here, so there's another way we could write this then. We could actually write it as 6.02 times 10 to the 23. And all it does is basically tells us how many zeros do we have after our value. It's a nice shortcut way of trying to make a very big number shortened up so we don't have to write all those zeros afterwards. And this is the slide I have to kind of help explain it. I'm going to skip this one and come to this one here. Okay. This slide right here is one that I found online that I think helps illustrate the point I want to make. Say that I gave you this thing right here. This is a yotta of something. You guys know about like kilos of things? You know, a kilo is 1,000 of something? See how 1,000 right here? 1,000 is 10 to the 3. Why is 1,000 10 to the 3? Well, look, because there are 3 zeros. So therefore, 10 to the 3. A mega something is 10 to the 6 because there's 6 zeros afterwards. Anybody have like a 10 gigabyte data package or a 2 gigabyte data package for like your cell phone? You guys have heard of gigabytes before though, right? When it comes to data? Well, a giga is 10 to the 9 of something, right? So 10 to the 9 means there's 9 zeros after the number. For anyone who has a lot of storage, I have a terabyte of storage at home on like a hard drive. A terabyte is 12 zeros afterwards. Okay. So that's all it does is rather than having to write out a really long number, we usually try to write it like this with a 10 power. We can also use this for really small numbers too though. This chart here, they've actually used a comma rather than decimals. But what this basically means is that 0.1 is actually 10 to the minus 1. Let's say you have a negative exponent. Negative exponents are actually small numbers. This has an exponent of 10 to the positive 6. That means you have 10 more zeros. If you have 10 to the minus 1, you have to remove zeros. So watch this. If I give you 0.01, this is 10 to the minus 2. This is the 1 that goes right here. That's 1 0. See how there's 2 zeros right here? Well, that's 10 to the minus 2. So long story short is this is a quick and easy way for us to work with really large or really small numbers if we need to. And why might we need that? Well, because when we measure a mole of something, we get 10 to the 23. We get a massive number of it. Okay. Here's an example. Let's just walk through these, make sure everybody kind of gets the idea. There's actually an error on this slide. So for anybody who normally likes to write things down, if you're copying them down, make sure you catch the error here. I'm just going to stand at the back so I can see better. So take this number here, 608, 000000000, right? Massive numbers of 0 at the end of the example. Well, what we could do, this is why there's a mistake. There shouldn't be a decimal place right here. We should just call it 608 times 10 to the 9. Because look, there's 3 zeros here, 3 more for 6, 3 more for 9. So just remove all those zeros and make it times 10 to the 9. And what was left? 608. That just makes it shorter. Some calculators will actually write it as, again, I have to change this. They would write it as 608 E9. E on some calculators refers to basically just how many zeros to add afterwards. Check this one out here. This one actually was written properly. This was 1.6 E minus 6. Because check this out. There are 1, 2, 3, 4, 5, 6 zeros in front of it. So the negative just means you have a really small decimal number. That's all. Okay, so why was this all important? Oh, I forgot a slide here. I should talk about this slide. You guys ever had to do the up and down the staircase thing in like a math class before? Where I think we just discussed this, where like 1,000 of something is a kilo, or 100 of something is a centimeter. It's basically the same concept. It's just rather than writing it as 10 to the 3 or 1,000, we would just write it as 10 to the 3. It shortens it up a little bit. So, okay, so let me go back to my point, because all of that was a bit of a brief aside. We are now talking conceptually about trying to add up how many things we have. Here, I'm going to sit here if it's okay for a little bit. Okay, I can see while I work. We can count things up individually, one at a time. We can count things in a dozen, but we don't use a dozen. 12 is not enough. 100 is not enough. We need 6 times 10 to the 23. That's what we need. And we call that a mole. Okay. Let's do an example of this here. Okay, so this example is one that's just sitting right here. I've actually even got the answer there. If you have a phone, actually, you know what? I'm going to move to the front for this one because I need my phone. Let's say that I told you that you had 4 moles of magnesium fluoride. My question is, how many molecules would there be? Let me just change the context of this a little bit. Let's say that I told you that you had 4 dozen donuts. How many donuts do you have if you have 4 dozen? Hopefully in your mind you're going, okay, 4 dozen, a dozen is 12, so 4 times 12 is 48. Well, you're more or less doing the same thing here. If I told you you had 4 moles of magnesium fluoride, you take 4 moles, you times by the official number here. It's actually 6.02 to the 23, because you know how that number was 602, 000 with all those zeros afterwards? All those zeros there. I can't even write them all. That's why it's 6.02 to the 23. Okay. Well, if you multiply those together, you'll get your value. I need you guys to take out your cell phone or a calculator, whichever one you have. It doesn't really matter. But I want to show you how to do this on your cell phone or calculator. Okay. So I usually have to turn my calculator sideways to make this work. Here's how I would go about just confirming this answer. I would take 4. I'd take 4 moles, and then I would multiply by 6.02. Now, some calculators actually have that E button on it, but it has to be capital E. Okay. I want to point out a couple things. My personal calculator right here has a little e right here and a second little e right here. That's actually not the same thing, sorry. I can explain that to you if you'd like at another time, but it has to be a capital E. So since mine doesn't have a capital E, I'm just going to write it like this, 6.02 times 10, and then if you have this button here, x to the y, what's happening? Oh, okay. Can we stay focused, though? I've only got another 20 minutes here to finish. I know, but I think we've seen a truck in a field before. This is new. Okay. Seriously? We need the x to the y button, probably. That'll give you the power, and then the power is 23. Okay. Now I want to show you what my calculator gives for an answer here, just to make sure you understand it. It wrote it as 2.408000, but like the calculator didn't want to write all of the zeros after this big massive number, so that's why there's the E right here. What does E mean? Just it means how many zeros are after this value. And then the positive means it's a very large number. So basically we need to add 24 zeros after the 2.4. One way of thinking about this is just move your decimal place over 24 times and just keep making your number massive until there's a huge number of zeros. Okay. So if you're struggling with being able to do that on a calculator on your phone, can you let me know later? Because I will try to help with that. Let's try another example though. So here's my second example. Let's say that we have 3.7 moles of calcium carbonate. How many molecules are there? Can I start with the first question? Does it matter that it was calcium carbonate? Let's say that I wanted you to have 12 dozen donuts. Let's say that I wanted you to have a dozen donuts or a dozen eggs. Does the fact that it's eggs versus donuts make one bit of difference? No. Right? Like if I gave you a dozen pens or a dozen kids in a classroom, either way a dozen is 12. So I want to point out the fact that it's calcium carbonate makes no difference one little bit as to what it is. So all we've got to do then is just take 3.7 moles and multiply by 6.02. I like to write it this way, E23, because that's kind of the shortest way of doing it. On your calculator then it would look like this. So follow along. Where'd my phone go? Here it is. You'd take 3.7 and you would multiply by 6.02. Since I don't have an E button, I'll just have to do it the long way. Times 10. Oh, don't want to disconnect. Go away. There we go. 6.02 times 10. Use the X to the Y button. And if you don't have something similar on your phone, just ask me later and I'll try to help you out here. But this will give us the exponent button and 23. Okay, one thing I want to talk about here. This is what confuses some kids. They'd say, we started with 3.7. Okay, so 3, almost 4. We multiplied by 6, and we got 2. That's what some kids look at. They go, Chris, how in the world can 3.7 multiplied by 6 give me 2? Smaller than we began with. But you got to kind of consider the exponents. This was to the power of 23, so it had 23 zeros after it. Our new answer has 24 zeros after it. So even though the starting point of the number looks like it's smaller, it's kind of like if I could write this on the board, if I were to give you 6 times 4, and you know that 6 times 4 is 24, right? But you'd say 6 times 4 somehow gives you 2, but you forgot about the fact that you get a whole other digit afterwards, right? Because you're actually adding zeros afterwards. That's really what's happening here as well, is that this went from a 23 to a 24. It's a bigger, because there's another 0 on it now. So, all right. That make a little bit of sense so far? We'll work on it. I don't need it to be perfect. So, my board just keeps glitching out on me when I move. This is a pain. I don't know why it keeps stopping on me. Come on. There we go. Okay. Oops, I said bash into things. Okay, let me go back and now talk about the weight concept. So here's that picture of where I was talking about weight for a little while here. So you can go down to Bulk Barn and you could buy banana chips, but I don't think it makes sense to buy banana chips one at a time. I don't even think it makes sense to buy banana chips 20 at a time. I don't even think it makes sense to buy banana chips 6 kabillion at a time. It makes more sense just to scoop a random amount into a bag and to just weigh it and just pay based on weight. Will every single banana chip weigh the exact same as the one next to it? Probably not the exact same. This one could weigh 1.1 grams, this one could weigh 1.2 grams, this could weigh 1.3 grams, but at the end of the day, like, doesn't it just kind of even out in the end when you're averaging things? That concept really applies to chemistry as well. I'm going to throw a new page in here and try to explain something here. Let's say that we talk about a single copper particle. Let's go with that. I guarantee you that copper has a 29 in the corner. It has to. That's what makes it copper. But some coppers weigh 60. There are some coppers that are still 29 because they have to be 29, but they weigh 61. And there are some coppers that weigh, say, 62 or 63 or 75. This top number up here in the corner, it can change. Okay. Now, the name we gave for this number up in the top corner here, we call it a mass number. Okay. But if we're going to be grabbing a whole scoopful, a whole 6 kabillion grouping of particles, I don't think that every single one of them is going to be a 60 or a 61 or a 62. What normally happens is we get an average of all those numbers. And that's actually some of the numbers that are on your periodic table. If you have a periodic table, can you grab it? Because we're going to want it over the next few minutes here. So grab a periodic table nearby. Okay, so I'm going to write a whole bunch of different possible copper atoms out here. Here's some copper that is either a 60 all the way up to 65. And all of these are copper because they have 29 protons, but they have different numbers of neutrons, though. Now, on your periodic table, though, if you look a little closer, on the periodic table, stay with me, please. Copper actually has a number on there, 63.55. I haven't talked about that yet, but if you can look on your table, see whether you can find how in the square for copper, there's the number 63.55. Here's how that works. When you are bringing not just one atom, but 6 kabillion atoms together, this is the average. The average of what all of them happen to weigh. So one at a time, copper either way is 60, 61, 62, 63, 65, right? But on average, the average kind of falls somewhere in the middle here. Just like buying banana chips. Does any one banana chip weigh the exact same as all the ones next to it? Probably not. But on average, when you buy a lot of them, this is what it turns out to be. The vocabulary that we use then is these things right here are known as just like a mass number. And sometimes they're called atomic masses. And the reason we call them atomic masses is because we're literally weighing one atom. Can one atom be a decimal number? No, because it has to be either 22 or 23 or 64. But if you get a decimal number like this, the 6355, the name we give for this is called a molar mass. And the reason we call it a molar mass is that it's the average when you have a mole of something. Okay. So when you have 6 kabillion particles, this is how much, on average, they weigh. I want to go to a slide right here to talk about that a little bit. I like this picture right here. We know that different particles have different masses. Okay? All of these right here are the same number of particles. Look at them. They're all about the same amount of stuff, right? Like the amount of white powder here is about the same as the amount of black powder, is about the same as the amount of silver stuff right there. But what's weird about it is that different elements, they all weigh a different amount. And the reason why they weigh a different amount is it depends on how many protons and neutrons they have inside of them. So this is the third way that we measure things, is based on how much they weigh. Lead, for example, right down here. Lead is one of the heaviest substances we have on Earth. Look at this little bitty bit of lead here. It may not seem like that, but that weighs 200 grams. Look at this. This magnesium that's right above it here, if you were to like just look at it, I would say that it almost looks like there's more of the top one than the bottom one, doesn't it? Like this top one right here, it almost looks like there's a little bit more. And yet, although there are an equal number, or at least roughly equal number of particles, this bottom one here weighs more just because they're heavier. There's more stuff stacked inside those particles. A lead nucleus has 82 protons. Magnesium only has 12. So that's the final thing we want to discuss then, is how do we figure things out based on weight? So that's the term I use here. It's called molar mass. Okay? Every item that you buy at, say, the bulk barn. So here's a picture of the bulk barn, right? Every item that's there, it all has a different mass to it, right? Flour could be really heavy, whereas macadamia nuts could be really light. I'm going to try standing here again so I can look at the board. Imagine then that you want to buy some carbon. Well, individually, carbon, I guarantee you, has to be number 6 in the corner. Has to. But one carbon particle is 12. But there could be another carbon particle that's a 13. There could be another carbon particle that is a 14. There could be another one that's back to 12 again. Then there could be another one that's a 12 again, right? Now, if you're doing this one at a time, it has to be a whole number. What's the word we give to that number? The atomic mass number, the mass of one of them. But let's say you're going to the bulk bin and you're taking a whole bunch all at once, right? Well, now will it average out to a nice even number? No. Carbon averages out to 12.011. Okay. So what we're going to work on now is basically calculating how heavy or how much there happens to be in like a compound or in an element. And here's a really basic example. If you have a periodic table, look up sodium. Okay? Sodium could weigh 22 or 23 or 24, but on average on your table, sodium weighs 22.99. Okay? It's really just a retrieve, right? Find a table, find the symbol, and it's the number that I've always kind of glossed over, but there's that number in the corner. That's how heavy on average sodium is. Oxygen also weighs a certain amount. Oxygen weighs on average 16 grams in its mole, and hydrogen weighs 1 gram per mole. Remember that picture I showed you there of all the different like powders, and they all weigh different amounts? Sodium is way heavier than hydrogen. Right? Imagine that I were to give you 20 items of something. If the 20 items were lead bars versus feathers, I still have 20 of them, but feathers don't weigh as much as lead bars do. Right? That's basically the concept here. Hydrogen is very light. Okay. Let's try an example together. Let's try to find the molar mass of sodium sulfate. What I'm basically saying is, tell me how heavy it would be to go to the chemistry bulk barn put together the recipe for sodium sulfate, tell me how heavy it would be, because everything weighs a different amount. Okay, first thought, what is sodium sulfate? Like, how do I even write its formula? Okay, well, sodium is Na. Sulfate is SO4. Those don't fit together though, eh? So again, you need a data table pretty much at all times. If you don't have a periodic table, you're kind of wasting your time. But hopefully you can find this. Sodium has a charge of +1. Sulfate has a charge of -2. Do these things two fit together? No. So I'll put a little 2 down here in the corner. And if I have 2 sodiums to every sulfate, now it fits. So here's my silly analogy. Mom wants you to go down to the store and buy the stuff you need to make sodium sulfate. You need to grab 2 of those, like, you know how you fill the bag and then you twist the tie on it, you write the little code on it? Right. She wants you to get 2 pouches of sodium. Oh, my board just keeps glitching out. Okay, going with the other one here. There we go. Okay. So let's say we want to buy 2 pouches of sodium. How much does 1 pouch of sodium weigh? Well, I think we just looked it up. It weighed 22.99. And you need to buy 2 of them because there's a little 2 sitting here in the corner. Okay, do some searching and finding information on your periodic table. How much does a sulfur weigh on average? Did we find that on the table? How much does sulfur weigh on average? Find it? What'd you find? Perfect. 32.0. Is it 6 or 7? Oh, I thought it was 7. Yeah. What, is there a number after the 6? Oh, interesting. Apparently there's a discrepancy between tables. My guess is it's probably 6.5, and it probably some tables rounded up or down. Since everybody else has got a 7, we'll go 7 for now. Okay, slight differences, I guess. Okay, how many sulfurs does this molecule require, though? Just 1. Finally, we need to figure out how much on average oxygen weighs. Okay, if you look it up on your table, oxygen weighs 16 right on the dot. Okay. So here's what you need to do then. We would then need to take our phone or our calculator and add up and figure out what the grand total sum is of all of these individual portions. Oh, my technology is just glitching on me right now. Okay. Okay, so I'm going to take my cell phone. I'm going to take 22.99 times by 2. Times by 2. I'm going to add 3207. And I'm going to add 16 and times by 4. Anybody else get this? I got 142. Oh, goodness. This is not working at all. I'm like so stuck here. I got 142.05. I know my technology is not working here. Please still pay attention as best you can, though, because I gotta have to stand here and do it with my mouse right now. Here's what that means, then. If you were to try to make sodium sulfate, if you're trying to make sodium sulfate, the sodium portions of it weigh on average 22.99, the sulfurs weigh on average 32, and the oxygens weigh on average 16. But you need all of them together to make the molecule, so the grand total I got was 142.05. Here's what we would write for units. That would be the grams. So I mean how much it would weigh if you bought 1 mole. And a mole is basically 6 billion particles. Okay. Let's try another example here. I just have to do it from my desk, apparently. I'll try it like this, see if that solves it. What is iron 2 oxide's formula? Okay, iron's formula, Fe. Oxygen's formula, O. Does iron have more than one charge? Yeah, it must, because there's a Roman numeral right here. But what charge am I using? I guess the 2 version of iron, so this is +2. What's oxygen's charge? -2 if you look it up on your table. Do these two things fit together perfectly? This one's actually even simpler. All we have to do is take iron. We need 1 iron and 1 oxygen. And we're just going to add up what they weigh on average. So on average, iron weighs 5585. You just find that by looking it on your periodic table. Oxygen weighs on average 16 right on the dot. So put those two things together, and I can do this in my head. I don't think I need a calculator. That's an 8, that's a 5, that's a 1, carry the 1. It weighs on average 7185. And here's how we usually write that. We write it as 7185 grams in a mole. You still with me? Okay. I think it's time to point out one of my posters that I haven't gotten to yet here. There's an upside-down pyramid that's over there on the wall, which is kind of a nice model for things that you need to be able to, I don't know, skills that you might need to have. And I would say that most of what we're doing right now is actually in the bottom purple layer. Can you see where it says remembering, find or remember info? I'm not sure if you can see it over top of the popcorn box. But much of what we're doing in chemistry right now involves using your table and just finding what the number means, right? I found these numbers by looking up charges on the table, and I found these numbers by finding them on my periodic table, and all I had to do was add them up, and now I know that if I had an iron oxide, it weighs 71. Okay, let me go back to that picture I mentioned earlier here. All of these pictures right here refer to the exact same amount of particles. They all have about the same volume, right? Like none of these, there's like way more in the pile, and yet they all have a different weight. I would have guessed, just by looking, I don't know about you, but I would have guessed that this thing right here would have weighed the most, because doesn't it look like there's more of it? And yet, this one right here was the heaviest because it's more dense. Density is actually what we're kind of discussing here. Okay, that's where we're actually going to end our lesson for the day. Here's what I want you guys to do. If you have your phone, I need you to go to the reflection for our lesson. Monday, we're going to keep working on this skill here. But I've actually put in 5 questions for you guys to try to answer as a reflection. I'll try to bring it up on my phone one more time for you to see. Hopefully I can make this work. Okay, almost out of time here, so I got to go quick. Go to Moodle. And I really hope you've been doing all the reflections as we go along, because otherwise you've got a lot of catch-up to do. I really want these reflections for a couple of reasons. One, it allows me to know what you know, so that at the end of the year, when we have to calculate a grade, we can look back and say, okay, what do you understand? But 2, it'll help guide me on Monday when we do some practice on this. I want you guys to go find the last reflection we have for lesson number 7, the mole reflection, but I've made one change. Hopefully this will help be a little bit more specific about what I'm looking for. I'm actually going to give you 5 things I want you to talk about. Rather than just make it open-ended, I thought maybe what I'll do is I'll tell you what the highlights of my lesson were. You tell me what you do and don't understand. Do you feel like you understand the concept of a mole? Exponential notation, molar masses, and atomic masses. Do you guys see how I'm giving you a little bit more to work with this time? Okay, that's your homework. Over the weekend, write a reflection for me, please. Okay, thanks, everybody.